All right, here we go with problem number 5. All right, problem number 5 tells us that an astronaut stands on the edge of a lunar crater and throws a half-eaten Twinkie. Why a Twinkie? I don't know. Horizontally with a velocity of 5 meters per second. The floor of the crater is 100 meters below, that's going to be important, the astronaut. What horizontal distance will the Twinkie travel before hitting the floor of the crater? This also tells me, though, that the acceleration of gravity on the moon is 1/6 that of Earth. So this is a particular question where I cannot use negative 9.8 as my usual value for the acceleration in the y direction, but we'll see how that comes up. All right, so let's set up our problem. So I'm sorry, this is number 5. I should label that for you, except you can't see it on the screen. Move it down. Number 5. All right, so I want to make my x and y lists. A is 0. That is still true for the x direction. For the y direction, I'm on the moon now. And on the moon, the acceleration, it tells me, is 1/6 that of Earth. So to find the acceleration on the moon, I need to take the acceleration on Earth and divide by 6. Okay? So I'm going to get an acceleration value for the moon that is 9.8 divided by 6. Using my calculator for that, I get 1.63 repeating. So my value for y is going to be negative. I still need that negative because I'm saying that down is the negative direction, meters per second squared. Okay, I've got those pieces, and I've got a little bit more information. I also know that the Twinkie is thrown with an x velocity of 5 meters per second. And I know that the crater is 100 meters deep. So that means the Twinkie ends 100 meters below where it started. Okay? Because it's thrown horizontally, I also have my final piece, and that's that VIY is 0 meters per second. So as with the previous couple of problems, this one is a horizontal only velocity piece. All right, so let me go about solving it. I'm going to do the same thing that I did for number 4, where I'm going to use my y direction to find time first. So delta y equals VIT plus 1/2 AT squared is the equation that I'm starting with. I know, again, that VIY is 0. So this whole term is going to be 0. Okay? Knowing that, let's rewrite it to 1/2 AT squared. So I have 1/2 times negative 1.63 now, not negative 9.8 because I'm on the moon, not Earth, t squared. But my delta y I can replace with negative 100. Okay, so I'm essentially solving negative 100 equals 1/2 times negative 1.63 times t squared. Solving for t in my calculator, I get 11.1 seconds if I round. Now I'm going to plug that into my delta x equals vxt equation to solve for delta x. My Vx was 5. My time is 11.1 seconds. So I get 55.3 meters as my delta x. The answer key says 55.4 meters. Assuming small differences in rounding, we are good to go.